Hello. So today we're going to be talking about limits. But before I get into the exact, well, not the exact definition of limits, but what they are, let me just go ahead and talk about this function I drew here, or this parabola. It's just a parabola. So usually when we're graphing something, it can be whatever. It can just be a straight line, a parabola. It can be an absolute value line function too. Whenever we want to find, for example, like a point on the line, and the line is continuous, remember it has to be defined. If it's undefined, it usually, well, we just say it's undefined, or it's just, or it may be unbounded. But either way, whenever we want to find the value of a function, we just plug it in, and this is what I did here in this parabola or this function. I plugged it. First I plugged it in algebraically, so I just replaced x. I'm finding what the value of the function is at x equals 2, which is just 2 squared, and it was 4. So this was nice and easy. Of course, the parabola is defined. It's continuous, which means that it goes on forever. There are no like discontinuities. There's no just holes in my line. And this makes it a very consistent line, makes it continuous. But what if the function was not continuous? What if it was actually undefined? Let me go ahead and just make it undefined. And this is where we actually start talking about why limits are useful. So here, so imagine this is just a point that's gone from the function. Now this is not true. This cannot be true because this point is not defined. So this cannot be true. So what do we do? And this is where our answer leads us to limits. Limits basically talk about the concept of getting infinitely close to a number. And so for this specific function or that we're trying to find x equals 2. Basically, a limit just tries to find what the value of the function is as x approaches 2, as we get infinitely closer to 2. So for example, you can do this in your head too, um, or on a graph or a table. So doing this on a calculator, getting infinitely closer, just it means what it's a literal definition. So what I mean by this is you're not exactly at that point. You're getting closer and closer to x equals 2, but you're not actually there. Eventually, you're just so close that you are actually at that point. But let me go ahead and just do this before I confuse you anymore. So, getting infinitely closer, we can, for example, just say what's 1.9 squared? It gets us 3.61. Okay. What about 1.999 squared? It gets us 3.996. It's getting closer to what, 4. That and that is going to be our limit. Um, Let me just go ahead and write it here. So this is the, I guess you call it the fancy notation. So let me just do this. Lim is just short for limit, and we're trying to find the function, which is just x squared. I'm going to skip writing the function, just put in what the actual function is. So the limit as x approaches 2 of x squared. So once again, back to like the arithmetic, I guess. So getting infinitely close, you can just do what I said. You can just replace it and try to get as close as possible. You can get like the approximate answer, which does work, but it may not work sometimes. So I said 1.999 squared is equal to 3.996. I think I said that right. 1.99 squared, 3.996. Yep, correct. And then you can get even closer. This is how you get infinitely closer. You can now put 5 nines. I mean, so 1.99999. So now it's 5 nines, and then you can get 3.9999996. Yep, 4 nines. So just from that, you can tell you're getting infinitely closer to x equals 2 of that function. You can also do it the other way around. The way I just did it is coming from a lower value. You can also go from a higher value. So you can do 2.01 squared gets you 4.04. 2.0001 squared gets you 4.00000004. So 3 zeros and then a 4. So now you get my point, I think. So you can just keep on adding more zeros, or you can do it the other way around, keep on adding more nines, but you're going to be getting infinitely closer to that point, that value at the value of the function at x equals 2. Now, doing it algebraically, you can just plug it in. So limits as x approaches 2 of x equals of x squared, I mean, you can just, this is just equal to 2 squared. So the limit as x approaches 2 of x squared is 4. Now the value is the value of the function is not always the limit. Sometimes it may be. So for this function, right now it's not defined. I could define it. I could maybe like define it up here. It's ugly, but this is fine. I could define it up there. I don't know, make that like 10. Oh god, that's horrible. I don't know. Make that 10. So if I was just talking about the value of the function, I'd have to rewrite the formula. It's x equals squared as long as x squared, as long as x is not equal to 2. Whenever x is equal to 2, 10. That's our formula if we want to be accurate, but let me just go ahead and delete that. Just add that in real quick so I can be as mathematically accurate as possible. So here, the value of the function is not equal to its limit because we just solved the limit. It's getting closer to 4 every time we increase our x, and you can see it here in the graph too. It approaches x equals 2, and the number that it approaches is always 4. So that's just one example of a limit. Let me go a little bit more into detail. Here I already have some preset graphs, and what you're seeing here is just a function, and it could be a crazy function, whatever. It doesn't matter as long as you follow the limit rules. And I'll talk about some here. So let's do this. So the limits of as x approaches 6 of f of x. So once again, 6. This is perfectly fine. You're approaching a number. So as you get closer and closer to the value of the function at x equals 6, you get closer and closer to 1. And you can see that right here. Yeah, you can see this. And I'm not going to just draw the lines because I'm going to make it messy. So but for this answer is just the 1. So now, down here, the limit of, as x approaches 4 of the function of f of x, or the function, we go to 4. So once again, this is undefined, but remember, the value of the function is not equal to the limit of the function at that x, or at that point. So this is perfectly fine. We can find the limits, and in this case, it's 3. Yep, because once again, both sides are going towards the value of the function at x equals 4. Yep, x equals 4. So maybe you might be asking, why am I bringing up the fact that it's approaching both sides? This is where it becomes relevant, and this is one of the most important properties of limits, and well, not really a property, more like a rule or a law. So this last one. So the limit as x approaches to f of x. So we go to 2, but this is different. The value is the function is defined at 2, but there's something we call a jump discontinuity, and it jumps up. If you wanted to draw the function, the line here, you'd actually have to move your pencil and then jump over here, and then once again start drawing. And then this is just the point discontinuity. You like hop over it. But here, let's go ahead and use our both sides like strategy. So from the left, we're approaching 2. Okay? But from the right, we're approaching 5. This means that the limit does not exist. This limit cannot exist because you're approaching 2 different values as the function reaches x equals 2. So we just say this does not exist. Okay. And a little bit more in detail, I have it here. This is basically what I just did in my head. Limits can also be written like this. They can have a negative exponent or a positive exponent. It's not an exponent. It's just a way to like write a limit when you want to when you want to find where what the limit is from a specific side. And so what I wrote here is x as it approaches 2. This is negative because it's less than 2, so it's approaching from the left side of the graph, from the left side of the line graph of yeah the line graph of this line. So 2, it approaches from the left, and it's getting infinitely closer to x equals 2. This does have an answer. Whenever they're asking for specifics, they usually always do have an answer. So now let's find it from the right. So the limit as x approaches 2 from the right, positive. This means numbers are bigger. They're coming from the bigger side, bigger numbers of the function. And here, once again, we found that it was 5. So these individual limits exist, but however, this these individual limits do exist whenever you're finding like the sides they're coming from. But if they ask you for a definition as x approaches 2, just from both sides, this does not exist. Remember, in order for a limit to exist, it has to be approached from both sides. It has to approach the value. It has to approach the value of that function at whatever x you're looking for from both sides. And this is just the first lesson of limits. Next video I'll just talk about a few properties of limits. Thank you.